Hello, my name is Jessica Susi. In this project, I used regression to adjust measurements made on a mixed gas and liquid CO2 stream to better predict the mass flow rate and apparent gas content of that stream. The data I used were from experiments run at the University of Kent. What they did is measured the flow rates using these Coriolis flow meters of liquid and gas streams, mixed them, measured those flow rates, and tried to compare the actual flow rates from the single-phase system to the apparent flow rates in the two-phase system. The data set consisted of averages of 406 experimental runs, from which I had to cut 16 outliers. For example, there were 6 data points where the density of the gas was much higher than you'd expect at those temperatures and pressures. How they measured the flow rates in the system were using these Coriolis meters. They're quite special in that they measure mass flow rate instead of volumetric flow rate, and they can also characterize the fluid density. How they work is that the fluid is split into these two oscillating tubes. As fluid flows through the oscillating system, the Coriolis effect causes the fluid to twist the tubes and they oscillate out of phase. This phase shift is proportional to the mass flow rate in the system. Coriolis meters can also use the frequency of oscillation to figure out the density. In general, they're quite accurate for single-phase mass flow rates, but quite a bit worse for a mixed gas and liquid stream. So this is from data from my data set. It compares the relative error of the apparent flow rate measured by the Coriolis meter on the mixed stream to the liquid flow rate and gas mass flow rates. What we can see is that at really low mass flow rates, it tends to be not great. And then as the gas content of the stream increases, the error tends to increase as well. So my goal was to use the two-phase flow data with the apparent mass flow rate and the density to predict the actual mass flow rate and the gas volume fraction. For the mass flow rate, the features that were most highly correlated were the mass flow rate or the apparent mass flow rate and the time shift, which is how the Coriolis meter calculates mass flow rate. This is not terribly surprising. But in my models, I included the top 6 features. One thing that I'd like to point out is that the scale on this is logarithmic. So the mass flow rate really, really dominates predicting, or the apparent mass flow rate really dominates predicting the actual mass flow rate. This isn't super surprising, but for the gas volume fraction, these were the 6 features that I included in my models. Again, unsurprisingly, the density and the frequency, which is what the Coriolis meter uses to calculate the fluid density, are highly correlated to the gas volume fraction. This is certainly what I would have expected, but I also included the other 4 top performing features. So I used 6 different regressors, ones that we've seen all semester. The novel thing that I did in the project was include hyperparameter tuning. For something like k-nearest neighbors, it's pretty easy to guess and check maybe what number of neighbors performs best in your model. For something like a neural network, it's not obvious to me how to pick a good activation function and also figure out how many hidden layers to use, et cetera, et cetera. Hyperparameter tuning really helps with that. So what you need to do is split your data into training, validation, and test sets. Because my data set was quite small, I used 5-fold cross-validation. You need to give the tuner some objective function to minimize. What I used was the mean R-squared score across my 5-fold validation sets. You also need to tell the tuner where it can look for the hyperparameters. For XGBoost, it has many decision trees. You can specify a maximum depth. The default maximum depth is 6. I told the tuner to look at trees with a max depth of anywhere from 2 to 15. The tuning algorithm is what picks new hyperparameters to try out. In HyperOpt, the tuning algorithm kind of smartly notes which hyperparameters perform well and maybe looks in the neighborhood of those, rather than doing something random like random grid search. And then over something like 90 evaluations, it compares the scores reported by the objective function and finds the best performing model. So with my results in hyperparameter tuning, with some methods that performed quite well, tuning them didn't really improve them much more. The default XGBoost method did really well with predicting the actual mass flow rate. Tuning it caused it to do a little better, but I would really call these benefits trivial. In other models that I trained, the default was not great, but tuning it did improve it. However, even this tuned model performed worse than the defaults of the other 6 methods, or rather 5 methods that I tried out. So if a certain method is a poor choice, tuning its hyperparameters will not benefit you very much. However, in some cases, it really helped improve my models. The default neural network for predicting gas volume fraction was okay, but it was maybe not so great at these higher gas mass flow rates. By tuning it and figuring out better hyperparameters to use, I really improved the performance, and this ended up being the best performing model for predicting the gas volume fraction in the mixed stream. So the models that I would recommend for the gas volume fraction are either that neural network I was just talking about, or perhaps the linear model, which was performed very comparably to the tuned neural network. Realistically, it's probably better to choose the linear model. It's less computationally costly to train and test and deploy. So this is the model I would recommend. For the mass flow rate, the tuned XGBoost model did really, really well compared to the mass flow rates measured by the Coriolis meter. The mean absolute percent error was 4%. Tuning my XGBoost model reduced this down to an average of 1% error, which is very, I would say, acceptable. Here's some other figures that show that it performs quite well, even at these low mass flow rates. However, it maybe does just about as well, maybe a little better with high gas fractions. So in summary, I successfully created some models that can predict the mass flow rate and gas volume fraction in a 2-phase CO2 stream. In the case of the mass flow rate, it does quite a bit better than just using the flow rates reported by the Coriolis meter. Some caveats is that it's a small data set run on a single experimental setup at really specific conditions. Extending it beyond these would certainly require collecting more data. For me, the most important part of the project was learning about hyperparameter tuning. In general, the default models performed quite well, so I generally saw only modest improvements with a few cases of really significant improvements. However, these benefits tended to come with computational costs. For something like tuning the hyperparameters of the neural network. It took quite a lot of computation time on my computer to get that done. Thank you.